Sir, I have two questions for you. Most of the practical trusses, if you see, the self weight will be considered. So, in that case, how to proceed in analyzing the forces in the members?
So, if the weight of the truss members
weight of
have
the
to
truss
be
members
considered,
yeah.
how will you go about doing that?
Yeah. So,
Okay.
suppose one truss will be like this. Okay. So,
Okay. So, let's take.
If weight is considered, how to proceed further?
Okay. Good question.
So, this is one question. And the second question is like suppose one bar is with the self weight as well as it is subjected to external force.
Okay. Hinged on top.
Yeah, hinged on top.
Okay.
So, how to proceed for this?
It has self weight also.
It has self weight
Okay.
also. Okay.
The two questions are actually related. If I answer this question, this question can be answered. It is usually such that when you design the trusses, the weight of the members may not be as negligible. So, how do I consider the weight of the members also in my analysis and therefore in design? Okay. A simple way to go about is, supposing I take this particular truss, let us say its total weight is W, let us say this is A, B, C, D and E, let us say. So, WAB let us consider and ask the question, it is in between, so it will pose a problem. We will assume that the weight is not very high compared to the external loads that are applied. Okay. Okay, in that case, what you can do is you can take this weight, divide by 2 and equally divide among the two nodes of the member. For example, if this is AB and it has a weight equal to WAB, if these were hinge supports, then I will have reactions coming on it, and these are equal and opposite because these are equal to each other because the weight is in the middle, and therefore this will be WAB by 2 and WAB by 2. So that when I have to consider this weight, what I will do is I will remove this, distribute them equally among the two nodes A and B as WAB by 2, WAB by 2. You can do this for every member. For example, for this member I will have again WBC by 2 coming in here, there will be a weight here which is WBC by 2. Okay. I will have to add the other 2 which is WBD by 2 plus WBE by 2 for this particular node. Similarly, for C I have 2 members and therefore the weight of those 2 members have to be considered. Okay. Let me just use the notation that I introduced earlier in an alphabetical order. Okay. So, it is as simple as that. This will give good enough answers in most of the cases. Okay. Mind you, when you look at this particular stress member, it is no more an axial member, right. It will also have some bending. Okay. So, it is a beam, but connected through hinges in a way, alright. Coming to the other problem. So, once I push the values of the weights to the nodes, then it is a regular truss problem that I have to solve. Okay. Looking at 2 is also simple. I have something like this. Pretty simple. If I have a force F acting on it, also a self weight, okay. Let us say this is AB, self weight is WAB. You can do very similar to what you have done here in order to consider this like a truss member. Okay. Now, let me just make it a little more complicated and ask this question. Okay. This is a pet question of mine that will introduce certain doubts in the mind which eventually can be addressed. So let us say I have a link, another link, both are attached like this, okay. Let us say I have these two links attached like this and there is a force acting on this. Venkat, can you make one like this and give me so that I can demonstrate two members like this? Now this is a very simple problem. All I need to do is I know this is an axial member and therefore there is a force acting here, force acting here. They have to be equal and opposite because this is like an axial force member or a link member, and similarly the other one, let me call this as ABC, this is BC, and for AB at this node there is an equal and opposite reaction, which means this will be F and this will be F, no problem whatsoever, okay. So let us look at this particular problem a little differently. So he just made one like this for just illustration purpose. There is a force acting at the end BC. Okay. So this is A, B and C. So if there is a force acting like this downward, then I can resolve like this. What if there is a force acting like this? What really happens is if I hold it like this and pull it like this, you can see that the force automatically moves the member along the line of the force, okay. So let me make it even more difficult. Fine, this is the way it is. Now instead of a force acting downward like this, there is a force acting upward like this, and if I ask the question what is the force in the members, well that is not very difficult. I just have to put this force in the opposite direction, F, equal and opposite, which means it will be acting like this, equal and opposite, which means it will be acting like this, equal and opposite, which means it is acting like this, problem done. But if you notice carefully, if I apply that kind of force, it is perfectly alright as long as it is along the axis of both of them, but if I apply a little inclined way, it starts to, right, you can see it just goes. As long as it is completely axial there is no problem, but even a small angle is enough for it to collapse, or in other words for a small angle is enough for it to become a mechanism, okay. But how is it that I am able to solve this problem? Well, is it in equilibrium? Definitely yes, it is in equilibrium. But the problem is it is not in stable equilibrium, it is in unstable equilibrium. Supposing the force is in this direction, there is no problem, it is stable equilibrium. The moment the force is in the upward direction, even though I can solve for the equilibrium, please remember if there is a slight movement sideways, immediately it will become unstable, okay. And therefore please remember that a problem for equilibrium may be to do with unstable, stable or neutral equilibrium, okay. This is a perfect example of an unstable equilibrium, okay. A ball rolling on the ground is in the state of neutral equilibrium, okay. I still will be able to find out if this is the mass, I will still be able to find out what will be the reaction on that particular rolling bar, alright. Another interesting example is this, which is a wheel. This is a wheel, okay, and let us say it is rotating with a angular acceleration, angular velocity omega, okay. At this point, can I find out the force acting on this if this is an axle? For example, I am just going to make it a little easy to realize. Let us say it is fixed on an hinged on an axis, and this is rotating with a angular velocity omega, okay. Since it is rotating with an angular velocity omega, and this is a point on which the support is existing, can I solve this like a statics problem? The answer is yes. Plus, but please notice, any other point that you take apart from the center will undergo an acceleration, right, because you have m omega squared r that comes into picture, alright. There is an equivalent opposite reaction posed by the body, and therefore this particular particle is in equilibrium of the body, okay. Or in other words, if you take any other point on this, it is actually accelerating, okay. But this is a problem where I could simply solve like a static problem, okay. And if this is very similar to the rolling bar that we have introduced over here, okay. So please remember that it can be stable equilibrium, unstable equilibrium, neutral equilibrium. As long as there is equilibrium, or in other words there is a statical notion that I am able to bring, it is possible to solve for the forces, okay. One other important thing to note is, how do I know it is stable or not, okay. It is like asking the question, how do I know a person is sleeping? What do? I go find out whether he is responding to it, or just tap a little bit, check up, right. So we disturb the person to a certain extent to find out whether the person is sleeping. Very similarly here, I will disturb this a little bit, I will just move the force this way, that way, find out if it is coming back to the configuration that I have. If it is so, it is in static equilibrium. If it is not, but still it is holding in place, it is in neutral equilibrium. Or if it is applied upwards, as you have already found out in this particular example, slight change, and if I push, it becomes a mechanism, okay. Or in other words, it is no more in static equilibrium, okay. We have a truss like this. If you look at it, quite a few members are there, okay. This is a truss in which you have small members like this connected to these bars, and there are some forces acting on it. I have just numbered all the joints, okay. All the joints are pin joints, okay. Now, if I ask the question, are there any members in this which are members with no force at all, okay, we call those members as zero force members. Okay, let us examine and find out whether we have zero force members, okay. We notice here, this is a 10 kilonewton force acting at C, and you have a bar over here and two bars over here, okay. Let us examine this particular node. If I had taken a section of this joint, I would have revealed the member forces. Let me just write them down. This is JK, HJ, IJ, okay. Upon examining this, immediately one would find that vertical equilibrium will involve only Ij, the member Ij. There is no external force acting on it. If I take sigma Fy equals 0 for this immediately will give me an answer that Ij is equal to 0. Okay. So, this is a 0 force member. Okay. Let us say this is connected in such a way that this is perpendicular. Okay. Is this a 0 force member? Well, if I had found that Ij is a 0 force member and this is perpendicular to this particular set of members Kij, and if I draw the free body of this particular joint I have 1, 2, 3 and 4 forces revealed. Mind you, I am always drawing in such a way that all the forces emanate from this joint. Okay. So, now I just have to number, this is Ik, Ij, Hi and Gi. Okay. What did I do earlier? I looked at this particular joint and found that member Ij is a 0 force member. So, this is a 0 force member. So, let me just erase for the sake of understanding. Okay. And what is this angle? This is perpendicular. And if I take this as let us say y prime and this as x prime and find out sigma Fy prime equal to 0, there is only one force that will take part in it, there is no external force also. This immediately tells me that member force Hi is equal to 0. Alright. So, let me use another color here to indicate this is equal to 0. If these two are equal to 0, how about these two? Can I say anything about it? I am tempted to say that Ik and Gi are equal to 0. Please do not do that mistake. Remember, Gi and Ik are equal is a good answer, and therefore another point to note here is Gi equal to Ik is the other equation that I get out of this particular joint I. Okay. Like that I can proceed. If this were 0, Hi were 0, there is a force acting on this particular node. So, if I take vertical equilibrium, GH will immediately be equal to 20 kilonewton. So, it is possible to solve for this, which means this is a non-zero force member. Let me just put a cross to indicate that it is non-zero force member. Now, let us look at any other particular joint that will give us 0 force. Okay. If I look at this particular joint, I have equilibrium in the horizontal direction involving these two, vertical will involve these two, which means this need not be 0, this need not be 0. Okay. If this is not 0, this will have a component in the horizontal and vertical directions. So, unless I get something out of this, I may not be able to say anything. This is not a 0 force because there is a 10 kilonewton acting. If this is not a 0, this is not a 0 force. Okay. And naturally, if this is not a 0, this is not a 0, this is not a 0 force member, and so on. So, I can easily find out what are the 0 force members. Simple. But then supposing I ask this question in a particular construction, let us say these are the loads that are applied, why would I want 0 force members? This is an important question that many people fail to ask or answer. Okay. that is when you need to understand the stability of these particular members. For example, can you give me a long sheet, a long strip? Yeah, you can come over here. So this is a long strip, let us say this is under compression. Okay, if this is under compression, it easily buckles, we call this buckles. Just hold at the center, hold at the center, and I am going to press. When I press, you will find that I need to apply more force in order to get this member to buckle, okay. Or in other words, if I have to improve the strength under compression, under buckling, I would want to insert a member over here, that which will act to give stability to this, okay. A simple example that I can give is the same thing that we did earlier. Supposing I have something like this and a force is acting like this, it is already in equilibrium, but it is in neutral equilibrium. In order to make sure that it is fine in this particular manner, if I have to make sure that it supports the force in a stable manner, I may probably take one more member like this and connect it to a support, a horizontal member like this connected to support. And if you look at this particular problem, this is stable, alright. Even though the member, supposing I name them as A, B, C, even though member force BC is 0 in this particular case, it is very simple to analyze. Just like what we did in the previous stress, if I take a particular direction equilibrium at B, for example horizontal equilibrium, immediately I will know that BC member force is 0, this member force is 0, okay, and this member force is minus F, or in other words it is under compression. What is the action of this? The action of this is to give stability, else it will just freely rotate, okay. So many of the times in trusses you will find for certain forces, set of forces, there will be 0 force members. Most of the times these 0 force members are used in order to reduce the effective length or to give stability to this particular truss. In this case I could have had a straight member like this without this. Since these two are 0, if I remove them, I could have had something like this, but remember this has become longer, and if this were in compression, for example if there is a force acting on this, in fact this particular force will push it. If you analyze for the problem that is given already, you will find that this member is under compression and therefore likelihood of this buckling is more. So I would want to support it like this to a particular point, nearby point, and this particular member this is joint A, B, C, D, E, F, G, H. HI member is primarily to support the member GK, okay. Similarly you will find that this is under compression, okay. I will introduce another member like this. This increases support for this particular member as well as this particular member, okay, and that is the reason why you still have 0 force members in the truss, and it is useful for the construction. The main reason for that is in order to introduce stability to the truss. Thank you.